both technical, maybe some technical details for you to read some papers to better support our customers in the future. And then also give some progress we have achieved so far in our Japan team, because it's more like the first time to share the details what we have done in the former several months. Yeah. So title, as you know, is creative AI. So I formally call it creative AI, but I also like it to be generative AI. But basically, it's about to generative something from zero, right? So the image, text, a novel, poem, and all this stuff, video, you can imagine. So basically, another topic is latent diffusion model. So, you know, in recent years, there are so many models. The GAN, adversarial network, VAE, autoencoder, and also flow-based models. But it turned out that diffusion model achieved the best result, amazing result. You can see from a lot of news in this maybe last year, this year around. And most of this talk is based on our paper. We published this paper in coding this year workshop. So you can check. I will share the slide later after the talk. Yeah. So if you're interested, you can check more details. Yeah, this is a result, just the first image. So what we have achieved is like, so the target is that we, instead of generate photo style image, so we ask thousands of artists who lived maybe 100 years before, such as Van Gogh, Monet, Picasso, so many famous people. So we want to learn their style of writing an image, of drawing, of painting. So all these are based on these famous masters. So we want to go in a kind of different way instead of just generate a photo style thing. The photo is fine. So everybody can draw a photo, but if it's like the creation from a master, which actually can give a good hint of to learn how they exactly write something for a new topic, right? So this topic is more like a development of a city from a fish valley. So basically, it's a change to a town city. That kind of text input. I think I like it. It looks very creative and with some artwork information. So yeah, let's go to the outline. There will be 5 parts. So the background, as I said. So to generate the image, we actually have 2 ways in technical. One is so-called DDPM. So I will focus on DDPM. The second is score-based model. A score-based model is rather more difficult to be understood of equations. So this time, because DDPM is used frequently in the stable diffusion, so basically I will use it. Yeah, maybe this one. Yeah. I will use this. Yeah. To explain the basic ideas, the DDPM. And also, we'll give some background introduction about stable diffusion. The third one is actually what is a latent diffusion model, or the detail of stable diffusion models, especially the work we are using these days. Yeah. And then I will give some a very brief introduction about the 2 directions we done for even make the LDM to be better, so that we can learn from thousands of artists instead of just the photos, right? Photos taken from camera. We're asking the people who draw by their hand, so what they have drawn, the style, all the details, how they kind of describe the real world by their mind, their thinking, and what is output from their understanding. So I will do this thing. So we use a WikiArt data site. I will talk the details later, and then give some examples. Yeah. So to begin with, just this is really a very overview. So if you have any question, please ask. Because I am also a learner, so I don't guarantee I give everything correct. It's just based on my own understanding. So if you are really familiar with this field, please give a hint or questions. So basically, for generative AI, the big direction, there are several technical engine we can think, technical support to it. So in 2000, maybe 14 or 15, there was a GAN, right? Adversarial training. So which has a discriminator and a generator. The generator tries to cheat the discriminator, right? So it's try to generate the image as good, as real as possible. This is the GAN. But the problem of GAN is that it's not stable when you train it, and it can cause mode clasp problem. So basically, what does this mean? This means that so you can give a text to the model. You say apple, right? You say apple as a hint. Actually, it gave you only limited output diversity. But GAN is by far the most researched field. There could be more than 200 or 300 GAN variant models, right? Circle GAN, DC GAN, sequence GAN, so many GAN models. And the second big category is, we call it VAE, variational autoencoder. So we have an encoder, we have a decoder, and we want to learn the distribution here. The distribution of the data set, for example, the distribution of the group of images. As a distribution, we can use a Gaussian, mixed Gaussian, and then we want to learn the mean and the variance of the distribution. This is the VAE. So basically, in our stable diffusion model, we will use VAE to encode the input image into a latent space, and then do the diffusion in the latent space. So I will give details later. So basically, this is the second category of generative AI. The third one is actually, we call it flow-based models. So what is flow-based models? You can imagine as a kind of, it comes from the water flow or some, in our NVIDIA, we have a TTS model named WaveGlow, which is flow-based model. Basically, it's kind of, you go from X is the image or it's a speech, and then you learn a distribution and you inverse it. So this network, these two network, the flow network, is inversible. It's a inversible network, yeah, which is quite interesting. So you have to be, this is the kind of a mirror of this network, and it limits the network selection we can use, right? So LSTM, so basically you cannot use it. It's only maybe CNN or basic linear models. It's inversible, but it turned out it's really difficult to train this kind of model, a flow-based model. Yeah. And now we comes to our major thing. We name it diffusion model. So we go from one side and go to another side, right? So the good thing of this diffusion model is that it can give us a diverse output and can give a stable training. Stable training is really important. Maybe you take 2 weeks, 100 GPU to train a big model, but if it's gone, you never imagine what it will turn out to be. It cannot converge frequently. But for diffusion model, it's much better. But even sometimes it cannot converge. It's a problem. So the most challenge currently of diffusion model is it's slow at the inference. So the Triton people in our headquarters already connect with me and other people in headquarters. We are talking about how to speed up the inference speed of diffusion models, because you have to generate the target step by step. So suppose you have maybe 100 times to change an image into a noise, a Gaussian noise, and to recover from the noise to a real image, you still need another maybe 20 or 30 steps. It's a Markov chain, right? So it's slow. So for GAN, you can generate one time, so one shot, right? So basically, diffusion model can be thousands or tens of thousands slower than GAN or other models, which is a big problem of diffusion model. So the Triton and other inference techniques are actually working really hard on making the diffusion model to be better. I think you already see Jason's email about it. They call it game changer. I also think that if we can make the inference speed to be much faster, then we can actually have a really big market compared with current stage. That should be a very good positive direction. And just to go more details to diffusion model. So I'm trying to give an intuitive understanding. So what exactly is diffusion, and how do we do it? So suppose we want to build a building, right? We want to build a building, but we never know how to build a building. So we only know that there are existing buildings in the world, right? We in Tokyo, you can take photos of so many buildings, right? And the way is to do diffusion. Yeah, we use a TNT here. We bloom it, we blast it into nothing, sand and content. And then every step we destroy the building, we learn how to construct it. This is basically the basic idea, right? So we do not know how to construct a building at the beginning, but we always know how to destroy it, right? It's easy to destroy something than to build it, right? To just give a TNT, TNT means a Gaussian noise, right? You put a lot of noise into an image. And then every time you put a noise, you observe the consequent change of the image. And until maybe after 1,000 times, it turns to nothing but a noise. It's a natural noise. So when you do the inference, actually you are only given a Gaussian noise. And we want to recover the building from the sand and concrete, right? From nothing. So basically, this is the model we want to learn. To destroy, we do not need to learn anything. The destroy is so easy, right? It's so easy for you to destroy anything, right? You just use some violence, right, to destroy it. But X0 is actually the given samples. For example, it could be an image, it could be a text, it could be a voice. The thing we want to do is put the noise consequently into the given sample until it changes the noise. And then we learn in the inverse engineering how to reconstruct the building. It's a basic idea of what is exact diffusion model is. It's actually, in finance, when you want to estimate the stock price, you never know the stock price because if you know it, you'll be Warren Buffett or even have more money than him. But the thing is that we still want to estimate the stock price of this stock either after maybe 1 year, after half a year. What should we do? Yeah, we add the noise, so-called the Brown motion or the Wiener process. We give all kind of simulation based on Monte Carlo, and then we recover the original X0. So basically, diffusion model was used more than 10 years or even longer in finance already. So yeah, it could be a good combination of this technique applied to AI now. Yeah. And this is another example. So the question is like, so how can we build a rocket as soon as possible? Yeah, so we can buy a rocket from SpaceX, but then what? So our target is not only to use the rocket, but we want to build it from zero, right? And the only way is that we buy one existing rocket, we factorize it into pieces again and again, right? We reconstruct it, we check the function, and then we factorize it again and again until we learn how to build the rocket. Yeah, but the real world is never that easy, but just to express the basic idea. So basically, we are given a lot of samples. We want to learn how to rebuild from these existing samples. So you want to learn the distribution of these samples. It is a way that we can learn from inverse engineering, right? You know, for a lot of country at the beginning do not have any rocket. They buy maybe from US, from Soviet Union, and then they try to break it into pieces, maybe like China, right? So we want to do this inverse engineering step by step, maybe take a decades, maybe 30 or 40 years until we learn how to reconstruct a rocket from nothing, right? It's kind of learning from existing thing, you break it, and then you reconstruct it, right? It's a basic idea. Now we go to some distribution, right? So if you have any question, you can interrupt me, of course. Yeah. So there are three distributions, three things. The first one is we call it P theta distribution. You know, theta means the parameter set we want to learn. Yeah. So say we want to learn how to build a rocket. Run this kind of all the design, 3D, CAD you can imagine can be a theta, can be an element in theta. But if you want to destroy it, right, this second Q is actually you are trying to destroy. We do not need to learn it. It's kind of hyperparameter. There's no learning parameter here. The second, it's only a TNT, means that it's only a Gaussian noise. Right? It's only a Gaussian noise. You're given an image, you put a noise in it, everything is random until you can never check out it's a human face anymore. This right to left is you are going to do the diffusion. Diffusion means you destroy it from a very good image into nothing. This first diffusion is to recover from the Gaussian noise, nothing, to a real human being. Also, there could be a textual prompt here, right? You can see that I want you to generate a photo of a 30-year man with maybe brown hair or something like it. This constraint will give a hint to generate this image finally. So this is the first. The second. Third one is what we call inverse engineering or reverse engineering. So it's like we want to learn from destroying. We want to learn from destroying. This from x0 to xt is destroying. We want its posterior distribution to recover from xt to xt minus 1. Right? This is more noise. This is with least noise. This is the third one. You can see there's no parameters here. Means that this is not learnable. Very important. We have three distributions, but only the first one is learnable. We only want to learn how to build a rocket, how to build a building, not how to destroy it. Destroy it is so easy. You can use everything, the hammer, the TNT to destroy it. But it's meaningless to learn the destroying because you can use Gaussian semantic distribution to add to the existing sample. Yeah, this three is actually the basic concept we need to learn, right? Basically, this is our target. We want to learn from inverse engineering. If you understand these three distributions, basically all the diffusion model papers, there could be hundreds now. It's not that difficult to learn. Yeah, all the things is how to build a better theta site and to build a different ways of TNT. Right, you can have different, we call it a schedule of variance to do it. Okay, so the problem is how can we learn it, right? We know the target is to build a rocket, to build a building from nothing. But how, right? How to learn? We know the target now is to reconstruct a rocket, right? So it's not that difficult. So, we have the diffusion process from this green one, right? So we want to learn is the red one. We want to learn this. This is our target. So we want to use the third, which is the posterior diffusion of the second, to learn the first diffusion. So this is breaking. This is destroying. This is constructing. This is constructing. This is breaking. And the way you break something, you can think it in another way is you are actually building it in a posterior way, right? You use a Bayesian equation here, which is not difficult. This is the second one and involved in the third one, right? This is actually very important. The third one will help us to learn the first one. Yeah, these three things, I think if you can have a sense of it, then today, yeah, I think it is good enough. Yeah. Okay, we go to some equations now. It's called the DDPM. But maybe one time is not enough for a talk. I can give another talk later. Yeah, because you can check so many tutorial in the YouTube, but not so many can give you such a detail. Even in our NVIDIA, we have a CVPR tutorial. This year it's 3 hours. So when you listen to it, you want to give up. You want to give up because it's not easy to follow their pace of talking, right? So it's a DDPM, yeah, denoisy diffusion probabilistic model, right? It's very important. It's proposed in 2020, yeah, 2 years before. So basically, we want to talk about the forward diffusion process. So it's a TNT, right? We want to talk about this. So what is a TNT? How to build a TNT? It's just nothing but a Gaussian noise. A Gaussian noise needs two things. The first one is its mean. This is its mean. The second one is its variance, right? If you have a mean, you have a variance, then you have a Gaussian. This is a multivariable Gaussian. So basically, this is a vector. The mean is a vector. The variance is a matrix, right? This is a unit matrix, right? And we have a list of beta t. Beta is kind of a variance, a lot of variance, right? Because we're using a isotropic Gaussian distribution. So basically, in the diagonal, all the variants are the same, right? So it's 1 times beta t, 1 times beta t, like that. So basically, we want to build this. There is no parameter here, no learnable parameter here. The beta t is a hyperparameter, means that we need to determine it before we train the model. The forward, as I said before, the TNT, we do not need to learn the TNT. We do not need to learn how to destroy a building, how to destroy a rocket. It's so easy. Even a child can do it possibly. Yeah. So yeah, so it's a one step. So from x0 to x1, we want to destroy it with adding some Gaussian to an image, right? And finally, the Markov chain is like this. You are given an x0 as the initial perfect image. We want to generate a sequence from x1 to x2, x3, until xt, right? And then you can, because it's a Markov assumption. So basically, xt only depends on xt minus 1, right? So x1 only depends on x0. So x2 only depends on x1. So it's kind of this. Yeah, so conditional independent. Yeah. This is very important. This is a forward diffusion process. It's a joint distribution here. Yeah. So when the t comes to be infinite, right? So it's xt. It's just a noise, nothing but a noise. You completely destroy the initial image now. And yeah, there's so many equations. Sorry about it. But you take one time to understand all the stuff, you will never be troubled by the equations anymore. Yeah. I will try to take more time to explain this one. So what does this mean? Actually, intuitively, it's talking about instead of suppose you have a 10-layer building. you want to destroy the first layer, the second layer, third layer, up to down. This is talking about we can jump. Instead of break the layer of the building, one layer one time, you can actually use a stronger TNT. The TNT is so strong, it can explore 10 layers one time. So it's jump from X0 to XT. X0 is the initial building, good building. XT is the destroyed building. So suppose 10 layers are destroyed, right? So it's a jump. So you do not need to put TNT 10 times to the building. You can use a larger TNT amount to explore the building one time, boom, boom. Then the 10 layers are gone, just like it. Because this jump is very, very important, right? So based on the Gaussian's good distribution, so one time, so accumulated distribution can be expressed in a very good form here. So I will skip the technical details, but there is a background good probability here. So basically you put two Gaussian together, it gives you a new Gaussian. And the new Gaussian's mean and variance follows this constraint. And through this way, we can go step by step. Finally, it gives us a good amount of TNT to destroy a building. Yeah. So we can control the level of damage here. Yeah. So because we can control the level of damage, then we can control the level of reconstruction. So the level of damage is not our target. The level of reconstruction is our target. So we know how to explore 10 layers one time. Then possibly we know how to explore 10 layers one time of reconstruction. So why do we do this? Because it can speed up the inference speed, right? So initially you have 1,000 times to destroy a building, but now you enhance the amount of TNT. You only need 10 times, right? One time you explore 100 layers. So the same thing happens when you do the inference. You are given a noise. So initially you need 1,000 times to recover the good image, but now you only need 10 times, right? Because every time you are recovering, you are building 100 layers in one time, right? This is the basic meaning of why do we do jump. So jump technique is very, very important when you want to speed up the inference of the diffusion models, right? I just want to give you a very big image. Instead of go to too much details of mathematics, we want to imagine what these masters think about, right? So basically, I think the basic idea is to jump, so to reconstruct 100 layers of the building one time. And now after we destroy the building, we want to learn from the inverse engineering, right? We want to learn. So how to learn it? We are building so-called the P theta. You know, it's the first distribution we described before. And the thing is that we should know is that in the second and the third distribution, there is no learnable parameters, right? There's no learnable parameters. There are only hyperparameters. So beta t is the variance, is only a hyperparameter. But now we want to learn the theta, basically how to reconstruct, how to construct a building is important now. Again, it's a Markov chain, right? So we are starting from the noise. Xt is the noise, randomly generated noise, right? Randomly generated. It could be an image with just a black and red point, black and white points, nothing else. You can never learn anything from it, right? It's just like you open a TV without any signal. It's like that. It's a universal radio or something like it. Yeah. And start from xt, we want to recover from xt to xt minus 1 until we reach x0. This is the way we reconstruct the building, right? And then it's a Gaussian. Then now important thing is that you can see there are two types of parameters. The first one is the mean. This is the mean. The mu theta is the mean. This mean is determined by two things. Xt is a current step noise. T is the time, right? Suppose you are building the second layer of the building, right? Then T is 2, this T also 2, right? And this is the first parameter we want to learn. The second is quite similar. It's a variance. It's a variance of the distribution. So basically, suppose you have 1,000 image, you can take the mean of every pixel, right? And also the variance of every pixel to check how the difference are among these 1,000 images, right? So if these 1,000 images are taken from a same movie, then they are quite similar possibly. But if this 1,000 image are taken from 1,000 people, every people randomly pick a picture, then we have a big variance. It means that it's more difficult for us to learn. So basically, what does this mean? So for example, you have 1,000 rockets. If the 1,000 rockets all are built from SpaceX, then actually it's easier for us to learn. But if the 1,000 rockets are from different countries, from China, US, Russia, so many countries, I think it's really more difficult for you to learn the distribution, right? Because it's not only one company now, it's kind of different regions people are thinking in different way. Even the target is to put a satellite, put something into the space, but now actually the way are totally different of some details. Yeah. This we call it reverse diffusion, or we call it reconstruction. So this is a very simple example. I also have some code to this. So if you want to check the code, I can share with you after the talk. So basically, this is a forward we call trajectory. Trajectory is a very interesting word. So basically, it's the forward. So we are given this E as distribution, and we want to destroy it until we see nothing but a Gaussian, right? This is more like a Gaussian. But we want to recover it. We are given a Gaussian. We want to recover this E. Yeah. As you can see, there could be different direction to pay attention to. We call it a drifting term. Yeah. Drifting term is the mean minus the current noise, right? So how far we recover from the noise. Yeah, it's still some mathematical details. Yeah, if I do not express it, only give you the image. Actually, you can obtain the information from anywhere. Just to try to understand the third thing. Again, note that this is not learnable. There's no parameters here. Only we do is use some mathematical technique to, because this is a equation of 3 Gaussian, right? You use the Bayes rule is 3 Gaussian. And if it's 3 Gaussian, actually the result is also a Gaussian. In order to determine what the Gaussian is, we only need to know the mean and the variance, right? So we want to learn the mean and the variance, nothing else. So the learn means we can write the equations offline without asking our GPU to do it. So actually these two equations, these two items, the red and the blue, stand for the, this is for the variance actually. Yeah, the inverse variance, this is for the mean actually. Yeah, so we can times 0.5, it gives us a mean, right? Because you know, you can recover its x minus mu square, right? The mu is, the new mu is the mean. And then before it's 2 times sigma square. So it's actually the variance. It's very easy. So basically, if you learn some distribution of Gaussian, you can get this. This is not learnable. It's just a very easy way to obtain the distribution. But this is important. You see, it is inverse engineering. So we are given x0, we want to recover xt minus 1 from xt. Xt is with more noise, and we want to reduce the noise, right? Like this. Now we are going to, maybe this is a central part. So just because we are recording, so I think you can check later if you are not understanding it in one time. So target is the minimum negative log likelihood. Because we are using deep learning. In deep learning, you always need a target. the loss function. What is the loss function here? It's called negative log likelihood, right? Because frequently we want to maximum the likelihood equals to maximum the log likelihood equals to minimize the negative log likelihood. This is actually the likelihood, log likelihood for one sample x0. We put a minus here, and we are building using a variational lower bound here. This is a very frequently used skill. If you learn the VAE autoencoder, you should be familiar with it. So what does this mean? It's a KL divergence. KL divergence is always larger or equals to 0. So basically you plus something larger than 0, then this holds, right? So, and then you actually, this KL divergence equals to an expectation of this distribution given this function. This is f, this is p, the probability. Yeah. And then we go to some details. So what this going to say is that initially, how could we learn from the inverse engineering? P theta, remember, is our target, right? We want to learn step by step to construct a rocket. So Q is so-called the posterior of the way you destroy something, right? We want to learn from Q to P. So Q is given, is our diffusion process, and we check the diffusion process in inverse engineering, then we can learn P. Our target is try to make these two distributions as close as possible, just like this. So you destroy something by this way, and then you see how to recover it in this way. And then the recover network should follow your way you destroy it. Yeah, it's very smart idea here. This is expressed by equations. So sorry for giving so many equations. But actually, if you understand it once, you will never forget it because the idea is so smart, right? So instead of building something, you actually destroy it and learn from destroying. Interesting. More equations, but you should see these equations in a lot of papers. But just to give a conclusion here, there are 3 terms for us to learn the loss function. A VLB is a variational lower bound. 3 terms. The first term is actually xt. Xt is noise, totally noise, nothing else. So x0 is a given sample, the given good sample. Right? Basically, this is nothing. We do not need it. And the third term is about x0 to x1 can be merged into this second term. The second term is the most important. Let me try to explain again. What does this mean? So basically, p theta is the way we want to learn how to construct something, right? Xt is noisy, more noisy. Xt minus 1 is least noisy. This is our target. What we only have is the way we destroy it, right? The way we destroy it is from t minus 1 to t, actually. So here it's a posterior inverse engineering. So from xt to xt minus 1, we are given x0 as a hint. This is the initial building, and this is sometime we destroyed very strongly. This is something we destroyed very slightly. Yeah, so it is the least destroyed. This is more destroyed. We want to recover from the more destroyed to least destroyed. Just like you erase the noise from an image to recover its original form. And we want to do this comparison of these 2 distributions, which is the central, the most important part. Learn from destroying. Right? This is the posterior of the destroying. And this is the same thing we want to take as a target. If you learn this target, the diffusion model is never that difficult to you anymore. Yeah, you can do research, you can write patent, you can support better our customers globally and in Japan, because this is so important. But if you how to go from this to this. Actually, there are so many videos I can introduce you to you later. Yeah. So basically, I only used a Bayes rule, nothing specific. Yeah. So the second term is most important. Yeah. And so in the real implementation, we are not limited to predict the loss function directly. We use some slightly changed thing. So basically, there are three ways to construct your network. There could be three targets. The first one is you can predict the epsilon. What does epsilon mean? Epsilon with theta. You can see every time you see theta here, it means a model. It means a network, a trainable network. So what does this mean? It means that the noise, we want to predict the noise. Why? You can intuitively, you can think we want to predict the amount of TNT for you to do a specific level of damage to the building, right? So because when you want to explore a building, you need to know how many TNT to use, right? So if you use maybe 1,000 ton, well, the earth is dangerous, right? You have to be specific to be accuracy on the amount of strength you put to the building. It has to be controllable, right? Otherwise, it's a disaster. So basically, the first target is to predict the epsilon. Epsilon is a noise, which is very, very interesting. We are predicting the noise, right? If we know how many noise you added to an image, we can erase it to recover original good image, right? It's a good idea. The second one is actually predict the mu. Mu is the mean factor of the Gaussian distribution. Yeah, it's just like this, right? The third one is predict x0. X0 is exactly the target rocket, the target building you want to construct. Not that many people use this third direction, but if you know the DDRM, the DDPM, you will come to this idea. But I will skip it because time is very limited. Yeah. Basically, now we have updated LT now. So basically, ET is a kind of inference. Every time you generate a noise, the model try to predict the noise you are generating. So one very, very interesting thing is that epsilon t is used as the input of the model. And our target of the model is also to predict the same epsilon t. And this is really amazing. If you think about it, is that like epsilon t is the input of your model, and your target is also to predict epsilon t, which is actually fantastic. Yeah. So it's so intuitively thinking is that you're kind of transferring. So the model is also keep the original noise. It accepts a noise and you want to recover the same noise. So this way it's learning, right? So you're giving me a hint of how many TNT amount you used, and now I want to predict how many TNT you are used to explore a building, right? This is very, very interesting. Yeah, if you check the code, it will take time to understand why should people do it. Yeah, there's technical details here. Okay, it's the final page of all the technical details. So, yeah, so please focus. This is very, very important. Yeah. So basically, we can remove this part. Only keep the simplified loss function here. Remember, this is a noise you generated randomly at the time t. And this is the output of your model. The input of your model includes these three things. The first one is x0. The second one is time t, right? The third one is epsilon t you generated. So the alpha t with bar are hyperparameters. Alpha t bar are hyperparameters. You predefine them. So the model has three input, x0, time t, and epsilon t. Epsilon t is generated on the fly dynamically. It will predict the epsilon t. We want to make this difference from epsilon t, the noise, to the models predict the noise as small as possible. So we want to learn exactly how to destroy the building with very, very specific precision, right? If you know how to destroy something in a very controlled way, you possibly know how to reconstruct it from noise. Yeah, it's a basic idea. Then I come to the training and the sampling two algorithm. So even it's only 6 and 6 lines actually in the code, it could be tens of thousands of lines actually. So initially you have x0, you just pick it, you have a time t. Time t means that how many layers you want to destroy in one time, right? It could be xt, maybe the big T can be 1000, so you can have a uniform distribution. So one time you destroy 100 layers, right? 100 flowers, yeah. And then we have epsilon randomly generated from a Gaussian normal distribution. And then we use SGD to train it to try to minimum the distance between the epsilon you generated to the model's output. The epsilon here is used twice. This as a target and this as a model's input. This is very, very important. And after you train the model, actually it's epsilon theta. Epsilon theta is the model you trained. Epsilon theta is the model you trained. You can do sampling. Sampling means that initially you have xt, big T. It's nothing but a Gaussian. And then you can recover it. This is very important. This means that we are using the Markov chain to recover from T to 1, right? And then if you have a Z here, Z is actually, again, a Gaussian input. And then you can recover it initially. What does this mean? You can see xt minus the noise. So you are kind of erasing the noise. You are given a totally noise. You want to erase this part, erase that noise, erase this noise until you can recover to a good image, right? This is how we exactly learn the noise, the amount of noise in the image. We want to erase, to get rid of the noise from the noise, from the original noise image until everything is recovered from the noise, which is, we call it reconstruction. Yeah. You can see it's very slow, right? If T is 1000, you actually need a loop with 1000 to recover it. And then if we can jump maybe T divided by 2 and 1, 3 to 5 times, we can recover it. This to make the time of loop smaller is still a really hot topic of research in the field. Okay, I think I have 10 minutes left, so the following will be very, very interesting. Yeah, so the equations, sorry for the equations, but now we are going to be very, very interesting part now. So I have a code because formally we introduced how to generate the E, right? So here is S for Superman. So I have the code. If you want to learn the details, how exactly you put the hyperparameter, how exactly you use GPU, how exactly everything, you can see the code. It's only 200 lines. You get everything idea. Okay, so yeah, I think this part I will basically skip it, the details. Basically, it could be the image. We use autoencoder and diffusion and cross-rotation. They are not that important because cross-rotation appears so frequently in the transformer. And the unite, not that fresh, right? Unite is used for image segmentation in healthcare and a lot of domains. I think Colin is very familiar with it. So basically, I will skip the details here just to let you know what exactly are going on after we do it. So the inference, maybe one word, the inference is that we are using the pseudo-linear multi-step PLMIS algorithm. But in the original paper, they never give this good form. You can only see this equation in my paper. Yeah. So if you want to know the details, we can maybe arrange another time because time is limited. So basically, the basic idea is like we use a DDM to predict the x0, the current x, and then use it to do the inference. If you are familiar with stochastic diffusion equation, this should be not be a difficulty. And then I think this part is fine. So basically, if you are given urbanization of China, this kind of short query, we want to extend it to be with richer content so that we can ask the model to generate more fantastic, more interesting things. This is no big deal. Yeah, so this is a big deal, looks like. I'm using more than 1,000 artists from the recent 400 years to learn from them instead of generate the photo style image. We are generating something funny, more interesting. Yeah. So not that many people have not that many paints. So Van Gogh has the most, more than 1800, and other people, I'm not familiar with them, but if you are very good at art, you should know their name. So these are examples. So the former two lines are taken from the Stable Diffusions paper. We are using Van Gogh, asking Van Gogh, this line is Van Gogh, and this line, I do not know how to pronounce it, Shinsky, and Tissot, and Boris, We can have different style of generating something interesting. Yeah, so here comes something more interesting. So if you are given a text optimization of China, you can ask Van Gogh, a drawing this, a Chinese or Japanese style building, and you can see the high building here. This really tall square building with this all the things stuff. The Monet, you can see Monet style, not that exact drawing of all the building and the fish boat. And this is actually extended promote the text. So originally a collection of fishing village. So Shenzhen is a Chinese city. It rapidly grew to be one of the largest cities in China, right? I really personally like this one. You can see the fish boat here. Maybe it's sun or it's a moon. It's really a Van Gogh style, right? You can see the sky, Van Gogh sky. And you can see the buildings in the far view, right? And you can see all the things, and this Monet style. You can see the Monet is helping us draw the image, a modern world. Is that fantastic? I think some people may be interested in it. Yeah, because at the age of Monet, there are so many high buildings in his painting. Yeah, it's kind of, we are asking his experience of how to draw a modern topic. Yeah, I personally like this. This is about a train race on the snow-capped mountain. Right, you can see it's Van Gogh sky, and it's different people with Monet, so you can see everything is fantastic. So we can also have children running in a wheat field, right? Wheat field. I think this again, you can see the Van Gogh sky. I see children running here, different style. It's more like oil painting, and this again a Monet scale skirt. Yeah, because maybe he has several daughters, and he likes to draw the daughter in a boat. There are some famous painting of Monet, but now we are kind of ask him to redraw the image, the artwork based on the new prompt. We can actually do the high resolution with 1K times 1K. So again, this is Van Gogh. I forgot who draw this, but actually I personally really like this. Yeah, you can see if you see nothing, you put the painted image and go to the museum. Maybe people will say, okay, this is good. Maybe you can maybe cheat, sell this in maybe a very high price. All these are generated. This is more like a Picasso style. Possibly, I think it is drawn from Picasso's hint. Yeah, you can see all the shadows of the tree. You can see the boats, people, the dawning sign. I think this is rich of creative generation and artistic science. I personally like this than the photos. Yeah. So many. Yeah, I think I generate maybe tens of thousands of images based on the new model. Yeah. And all the things, all the stuff are so fantastic. Yeah. Yeah, I have 3 minutes. So basically we have a workshop. So Vincent and Colin helped a lot on this workshop. This year we also have a workshop which co-handled with Colin. So there are several benefits. We have non-papers, and we appealed our NVIDIA Leva and Nemo, and also we obtained 3 free tickets. So basically, we are saving money for our company. So every ticket is cost $650, right? We're saving nearly $2,000. We can attend the meeting freely, which is a good pattern, right? Because frequently when we attend a meeting, we need to pay, right? But now we need to pay nothing. It's free. So Colin, I, and another people joined the Colin and they gave a good presentation. And we also appealed our product, meet more people from Oracle, from Cambridge, so many global people are interested in this creative or generative AI. Yeah, I think now we can go conclude. So basically, I briefly introduced the background of DDPM, stable diffusion model with some examples. Yeah, I hope you enjoyed. So there are so many inferences. You can check the more details. So maybe I cannot cover all the topics in one talk, but basically, I think creative AI, generative AI is coming. So in maybe for more than 5 years, I'm doing this topic. For example, generate music. I have several papers of music generating, singing, the Miku, singing, and the painting, and a lot of designing of haiku. Yeah, also I generated haiku before. Stories, novels. Yeah, I think all these directions should boost the usage of our customers to our hardware and our SDKs. Yeah, I think this should be a good direction. Yeah, so if you have any question, I can answer. Thank you for your time.
Yeah, thank you, Shanzhou. That was super interesting. The art you've created is absolutely amazing.
Thank you. Thank you, Scott. Thank you. Yeah.
I can imagine you have some super nice pictures on your wall from it.
Yeah, we have so many, Scott. So actually, I didn't put everything here, but actually, I personally like it. Yeah, we have so many. Yeah. Yeah, so many good things. But anytime if you want to learn more details, have more questions, because our customer are kind of paying more attention to this generative AI in Japan as well. So I think we can prepare, and if people come to us, we make sure we are prepared to give them a better service. And even in our headquarters, a lot of team. Mingyu's team, Mingyu's team is building more stronger, stable diffusion models. So they are going to release it. So also I kind of join partly of this work. And again, we wrote several patents already, so we can protect our original novel ideas. Yeah, thank you.
Yeah, it's great. I've seen many conversations around our CEO saying this is going to be the way to have so many more creators in the world,
exactly.
and connected with Omniverse. I think this is going to be a huge topic for us going forward. Yeah,
exactly. This is it's content generation. When we build the Omniverse, if we apply to the game designing, we want more, character designing, background designing. So all this designing actually need some people's hard work. But if we can use this stable diffusion model to give them some more hint, actually they can speed up the gaming development. And even in Omniverse, real world factory, I think it should help a lot to the real world. Yeah.
So with that, I know we're over time, but if anyone has a question, I think now's a good time to ask. Or, of course, we could take some time at another time later if that's better. But any questions right now?
Yeah. So I have some more questions. So thanks for
please.
It's very interesting. So you're the artist, so amazing. So,
not me. Thank you.
Yeah, my question is that do we have any environment or something that we can directly play with?
Yeah, I'm on the way of releasing the model. So basically, if you can wait, I hope I can release my current model this month. but you can take maybe, yeah, I hope to give you the model this month, but you can actually start to play from very simple code. Yeah, I can share the simple code to the difficult code. Most are easy to understood. So basically, I think the answer is yes. So for the current model, maybe I still need maybe one week around to prepare it. But at least there are a lot of models existing in our company and outside our company. So I will show you the resources so that you can play now. And then when my models are ready, I can share with you. Is that okay?
It's okay. Thank you.
Yeah, sure, no problem.
Amazing. So hopefully if we can share the, maybe process of training such kind of great model, so maybe we can boost the utilization of the GPU to the customer, I think. Yeah.
Exactly. Not only training, but also fine-tuning and inference. All this stuff will need a lot of GPU, a lot of work. I think it also give some challenge to our Triton server because, you know, the diffusion inference is actually not that quick. It's slow. Yeah. The slow is a good point. If we can, if it's our task, so on NVIDIA's task to make it faster. If we can make it faster, then, you know, the equal is coming. Yeah, nice.
Yeah. Also, so on asking the question, so I have a further concern. So whether I'm not sure whether do you know do you think this going to be applicable to healthcare industry? For example, for there are big problem for preparing data to train model in, especially for pathology or something kind of images in healthcare industry. So do you think it is possible using the generative model to create something?
Yeah, the answer is definitely yes, because I'm also checking some papers of applying diffusion models to healthcare images to better help the segmentation of image, to enhance image enhancement. There are a list of papers on this direction. So let me check them and share with you maybe, I'm not sure tomorrow, maybe this week, Friday, before Friday. So basically, if you also search the healthcare with healthcare with diffusion, you should have a lot of lists. So yeah, a lot of list of published papers. So basically, it's really a hot topic even in healthcare. You can imagine. So basically, people are trying to use diffusion model to better. The data side is limited, but the application is really strong, and it's really a big market. It's a huge market in healthcare, right? Every people want to pay for their health, right? Not all the people want to pay for the art, but maybe all the people want to pay for the health. It's required.
Exactly.
So basically, stable diffusion for healthcare. So many papers. Let me collect them, and also we can share the resources later.
Yeah. I see.
Yeah, the diffusion model not only has been applied to the image, but also recently there is a paper published which used the diffusion model to predict and design the 3D printing structure. Even the performance is better than AlphaFold in some tasks.
Nice.
So it has huge potential.
Exactly. Yeah.
So I think we should introduce the customer. But actually, how about the data quality? So for example, so as you know, healthcare has something concerned with the health, especially for maybe something like the life. So if we are generating something wrong to the to train the model, so I think that will be introduced the bias, right? So how can we affirm the the quality of the data? So any insights?
Yeah, it's a good question. So do you have any answer, Colin? I don't have a good answer here.
Yeah. So because even we are getting the whole stat image from maybe from the machine, maybe some doctor will also check the quality, right? So I think rather than data itself, so I think the quality and also the data quality is very important. So yeah, just be curious. Yeah.
Exactly. So yeah, one way I can think about it is that stable diffusion can give us a good high resolution image. So if your image is really with low quality, with very limited size, stable diffusion can give a good way to extend it to make it sure to be high resolution. This is one way. Maybe another way is like, the quality can be with different ways of evaluation, right? So maybe the amount is not enough. The direction of taking the photo, healthcare photo is not enough. There could be a lot of directions to evaluate the quality of the image. But for sure, I think we can discuss later with headquarters how did we do it and think about new ways how to leverage diffusion models to improve the quality of the healthcare images and the 3D, just as Colin mentioned, even in 3D
structure,
still. Yeah. So yeah, I think that should be a good way to beat AlphaFold.
Yeah, that's interesting. So recently, as other maybe something like the Tokyo One project. So the real problem is that customers don't know the workload, so we need to propose and broker to customers. So I think this is one thing that we can actually propose to customers. So yeah, interesting.
Yeah. Sounds great. Yeah, sure. We can.
Thank you.
Yeah, no problem.
Yeah, that's all from me. Thank you.
All right. Any other questions today? If not, I think we're 10 minutes over time, and that was a super great session. So thank you, Shanqiao.
Yeah, sure. Thank you, Scott. Thank you, everyone.
Nobu, you came off mute.
Amazing.
Did you? Oh, he's clapping. Okay, great.
Thank you.
Yeah. Thank you very much, Shanqiao. I appreciate it.
Thank you.
I'll just stop the
Yeah.
recording now. And
Okay.
yeah, once again, thank you so much for today's session.